Hello, I am B. Chiranjeev Rao, Assistant Professor at Sri Shankaracharya Technical Campus, Bhilai. Welcome to this lecture on AC Drive 2. In last lecture, we are discussing the various method of speed control of induction motor using AC drives. Today, we will continue from that and we will discuss about rotor resistance control of induction motor, speed control using slip energy recovery schemes and synchronous motor drive. So, first we will see rotor resistance control of induction motor. Speed control by means of slip variation can be achieved by employing a variable resistance in rotor circuit. In slip ring induction motor, three-phase variable resistance R2 can be inserted in rotor circuit as shown in the figure. The rotor torque curve of the rotor resistance control of induction motor are given in the figure. By varying the rotor circuit resistance R2, the motor torque can be controlled as shown in the figure. The starting torque and the starting current can also be varied by controlling the rotor circuit resistance, while maximum torque is independent of the rotor resistance. Speed at which the maximum torque is produced changes with rotor resistance. For the same torque, speed falls with an increase in rotor resistance. Advantage of this speed control is that motor torque capability remain unaffected even at low speeds. However, cost of rotor resistance control is very low compared to variable frequency control. Because of low cost and high torque capability at low speed, rotor resistance control is employed in crane and other intermittent load application. So, next we will see static rotor resistance control. In this method is used to regulate the performance of slip ring induction motor. This technique involves adding external resistance to the rotor circuit of the motor to control its speed and torque characteristics. It is particularly useful in application requiring high starting torque and variable speed control. Rotor resistance can be varied steplessly using this circuit shown in the figure. The AC output voltage of rotor is rectified by a diode bridge and fed to a parallel combination of fixed resistance R and a semiconductor switch TR, which is a transistor. The effective value of resistance across terminal A and B RAB is varied by varying duty ratio of the transistor TR, which in turn varies rotor circuit resistance. Inductance LD is added to reduce ripple and discontinuity in DC link current ID. Rotor current waveform is shown in the figure, where the ripple is neglected and each diode conducts for 20 degree each. Now, we will see chopper control resistance in the rotor circuit. The maximum value of rotor does not depend on the value of rotor resistance. However, the rotor resistance influences the slip at maximum torque occurs. A family of curve has been shown in the figure for variable resistance in the rotor circuit. So, as resistance is increases, the torque is also decreases, as you can see in the figure. With the development of the thyristor, it has become possible to use a chopper control resistance in the rotor circuit. The diagram is shown in the figure. A resistance connected across the output terminal of a chopper can be varied from 0 to R by varying the time ratio of the chopper. When the chopper is always off, the supply is always connected to the resistance R. The time ratio in this case is 0 and the effective resistance connected is R. Similarly, when the rotor is always on, the resistance is short circuited. The time ratio in this case is unity and the effective resistance connected is 0. Hence, by varying the time ratio from 0 to 1, the value of resistance can be varied from R to 0. The slip power of the rotor is rectified by a diode rectifier and is fed to chopper control resistance. A smooth inductor L is used in the circuit to maintain the current at a constant value. Any short circuit in chopper does not have effect due to inductor L. The value of the resistance R connected across the chopper is effective for all phases and its value can be related to the resistance to be connected in each phase if the conventional method has been used. The rating of the chopper thyristor decides the maximum rotor current of the motor. The speed range is limited by the resistance. The method is very insufficient because of losses in the resistance, but it is suitable for the intermittent loading such as elevators. At low speeds in particular, the motor has very poor efficiency. Because of increased rotor resistance, the power factor is better. The rotor resistance in this case is non-sinusoidal. The harmonics of the rotor current produce torque pulses. These have a frequency which is 6 times the slip frequency. The maximum torque developed is decided by the current carrying capacity of the chopper. So, the next method is speed control using slip energy recovery scheme. The foregoing discussion makes it very clear the method of voltage control and rotor resistance have poor efficiency, particularly at low speed, and find limited application. The slip power is wasted in rotor resistance either inherent in the rotor or connected in the rotor circuit. The power output of the motor is rather limited. On the other hand, if the slip power can return to the mains, the system can become more efficient and the capacity of the drive is increased. With the development of the thyristor static power converter can be used in the conventional and service control to recover the slip power to the supply for speed variation. The speed variation brings in the speed control. The rotor power is first rectified by a diode rectifier. The rectified voltage is fed to a line commutated inverter. The inverter applies a back EMF which depends upon the firing angle. The output voltage of the rotor diode must be balanced by the back EMF of the inverter. The machine operates at a speed where this balance is obtained. The figure shows the method of slip energy recovery. The rotary converter and motor generator set of conventional system are replaced by a diode rectifier and phase controlled inverter. The combination is called converter cascade. The diode rectifier rectified the slip power and give back to inverter. The feedback to the mains by the inverter. The phase control of the inverter brings in speed control. In this method, power flow from the motor to the line via the DC link, and therefore, only speed below synchronous speed are possible in case of static hammer drive. The AC slip power is first rectified by the 3-phase diode bridge. then back into AC power at line frequency by the thyristor inverter, and finally return to the supply network by means of a transformer, which brings the rotor circuit voltage up to corresponding value to the voltage of the supply network. The speed of induction motor is regulated by controlling the firing angle of the inverter. The gate pulse are provided by firing circuit synchronized with the supply frequency. Both rectifier and inverter are line commutated by the alternating EMF appearing at the slip rings and supply network respectively. Now, next topic is static Kramer drive. In chopper method of speed control of slip ring induction motor, the slip power is dissipated in the external resistance and is led to poor efficiency of the drive. However, instead of wasting the slip power in rotor circuit resistance, it can be converted by various schemes for the speed control of slip ring induction motor. The circuit configuration of static Kramer drive is shown in the figure. The slip frequency power from the rotor circuit is converted to DC voltage, which is then converted to line frequency and pumped back to the AC source. As the slip power can flow only in one direction, the static Kramer drive offers speed control below synchronous speed only. The slip power from the rotor is rectified to DC voltage by diode bridge. Inductor LA smooth the ripples in the rectified voltage V. This voltage V is then converted to AC voltage at line frequency by line commutated inverter. As the power flow is from rotor circuit to the supply, static Kramer drive offer constant torque drive. As stated before, this scheme is offer speed control below synchronous speed only. The speed torque characteristics of stator Kramer drive for open loop system are plotted for different firing angles. It can be seen that these characteristics are similar to separately excited DC motor with armature voltage control. The static Kramer drive are used in large power and compressor type fans, where speed control is within narrow range. Next topic is static Serbius drive. The main limitation of the Kramer drive discussed earlier is the operation at subsynchronous range, which is less than synchronous speed due to the diode rectifier. For the speed control both below and above synchronous speed, static Serbius drive is used. Here, two possible configurations to obtain such drive. These are cyclo converter static Serbius drive and DC link static Serbius drive. The super synchronous speed can be achieved if the power is fed to the rotor from the AC mains. This can be possible by replacing the converter cascade by the cycloconverter as shown in the figure. The cycloconverter allow power flow in either direction, making the drive operate at both sub and super synchronous speed range, where motoring and regeneration features. As the slip ring is either written or taken from the supply mains, cycloconverter static Serbius drive offers constant torque drive scheme. However, the converter becomes costly and has a complex control system. The DC link static circuit based drive with power flow to and for the rotor can be realized by replacing the rotor rectifier on the rotor side by means of a controlled bridge rectifier using thyristor as shown in the figure. This provides speeds below and above the synchronous speed. The effect of non-sinusoidal rotor current are present. In addition, the commutation of the bridge rectifier at very small slips, that is near synchronous speed, possesses different types of problem. So, either force commutated or artificial commutation of the thyristor is employed at and about synchronous speed. This method is shown in the figure. A current source inverter can advantageously employed to obtain a series drive. In subsynchronous speed control of slip ring induction motor, slip power is removed from the rotor circuit and is pumped back into the AC supply. In supersynchronous speed control, the additional power is fed into the rotor circuit at slip frequency. It consists of a one slip ring induction motor, two phase control bridges and smoothing inductor and a transformer as shown in the figure. For subsynchronous speed control, bridge 1 has firing angle less than 90 degree, whereas bridge 2 has firing angle more than 90 degree. In other words, bridge 1 work as rectifier and bridge 2 as line commutated inverter for subsynchronous motor control. The slip power flow from rotor circuit to bridge 1, bridge 2, then transfer, and then the slip power flow from rotor circuit to bridge 1 to bridge 2, then to transformer, and then goes back to the supply. For supersynchronous motor control, bridge 1 is made to work as line commutated inverter with firing angle more than 90 degree and bridge 2 as a rectifier with firing angle less than 90 degree. The power flow is now from supply to transformer, then bridge 2, then bridge 1 and back to the rotor circuit. The static circuit based drive with power flow 2 and 4, the rotor can be realized by replacing the diode rectifier on the rotor side by a means of control bridge rectifier using thyristor as shown in the figure. So, now we are done with the speed control of 3-phase induction motor using electrical drives. Now, we move on to second part of this AC drive control, that is synchronous motor drives. The speed of a synchronous motor can be varied by supply frequency variation similar to a induction motor. Variable frequency drive employing synchronous motor are receiving considerable interest. The stator of the synchronous motor is supplied from a thyristor power converter capable of providing a variable frequency supply. The rotor, depending upon the situation, may be constructed with slip rings where it conforms to be a conventional rotor. It is supplied with DC through slip rings. Sometimes rotor may also be free from sliding controls, that is slip rings. A synchronous motor can operate at any power factor by controlling its field current. For operation at unity power factor and lagging power factor, the inverter must be force commutator. However, if the power factor is nearly unity, the inverter size is reduced, besides reducing armature copper loss. For operation at leading power factor, the motor must be overexcited. The motor is in a position to supply the reactive power required by the inverter. In other words, the machine voltage can be used for commutation. The inverter in this case is load commutated. The load commutation is possible with cycloconverter and current source inverter and voltage source inverter. A self-controlled synchronous motor drive employing a load commutated thyristor inverter is shown in the figure. A large power drive wound field synchronous motor is used. Medium power drive also employ permanent magnet synchronous motor. The drive employ two converter which are termed here as source side converter and load side converter. The source side converter is a 6 pulse line commutated thyristor converter. The speed of synchronous motor can be varied by supply frequency variation similar to an induction motor. The apply voltage must be varied in this case also to have maximum torque capability and to avoid saturation at all frequency. A synchronous motor can receive its variable voltage, variable frequency supply from a cycloconverter or a DC link converter. The DC link converter can have a voltage source inverter to feed impressed voltage or a current source inverter to feed impressed current. Further, the voltage source inverter can be a square wave inverter with variable voltage or a PWM inverter with constant link voltage. These two types are shown in the figure. When self-control synchronous motor drive operates at leading power factor, thyristor of the load side converter can be commutated by the motor induced voltage in the same way. As thyristor of line commutated converter are commutated by line voltages, commutation of the thyristor are induced voltage of the load, here load is motor, is known as load commutation. A separate control of the inverter feeding a synchronous motor can also be used. In this case, the speed of the motor is determined from an external frequency obtained from a crystal oscillator as shown in the figure. The performance of the motor is similar to a conventional synchronous motor with problem of hunting for sudden change of the load. The multi-motor operation is possible here. This is rarely used with inverter feeding. Next topic is load commutated inverter fed synchronous motor. The inverter is a current source inverter employing thyristor T1 to T6. The commutation of the inverter thyristor is done by voltage induced in armature of the synchronous motor. A chopper is used to obtain a variable DC voltage VDS from the fixed source voltage V. The VDS is varied with VDL so that a required current is supplied to the DC link and therefore to the motor. During the motoring, the power flow from the DC mains through the chopper, DC link and the inverter to the motor. When the inverter firing angle is changed from 180 degree to 0 degree, the voltage VDL reverses. If chopper operation is also changed to make VDS negative, but less than VDL in magnitude, the power flow from the load through the machine, inverter and the chopper to the DC mains, giving regenerative braking operation. Due to the presence of LD, inverter is an essentially current source inverter. Therefore, each traction motor is fed by its own inverter. If there are 4 traction motor, 4 such inverter will be required. Further, because of the current source characteristics, the inverter can be connected in series, but not in parallel. Thus, when 4 traction motor are used, one alternative will be to connect all 4 inverter in series fed by common chopper. Now, next topic is voltage source inverter fed induction motor drive. The voltage source inverter fed induction motor drive developed to have self control using rotor position sensor or phase control method. 3 combinations are possible to provide a variable voltage, variable frequency supply to a synchronous motor as shown in the figure. A normal VSI with 180 degree conduction of thyristor requires 4 commutation and load commutation is not possible. The voltage control can be obtained external to the inverter using a phase controlled rectifier. The link voltage is variable. This has disadvantage that commutation is very difficult at very low speed. As the output wave is a square wave, the inverter is called variable voltage inverter or square wave inverter. As the output is a square wave, the inverter is called variable voltage inverter or square wave inverter. The second alternative is to have voltage control in the inverter itself using principle of PWM or PSM. The inverter is fed from a constant link voltage. A diode rectifier would be sufficient on the line side. This does not have difficulty of commutation at low speed. Very low speed up to 0 can be obtained. The third alternative is to interpose a DC chopper between the rectifier and the inverter as shown in the figure. Thus, the system may appear the 3 simple converter are used to give desired result. It is possible to reduce the size of the DC link inductor by using a synchronous control of the chopper. Next, we study synchronous motor fed from a cycloconverter. DC link converter is a 2-state conversion device which provide a variable voltage and variable frequency supply. Variable voltage and variable frequency supply can be obtained from a cycloconverter, which is a single stage conversion equipment. The power circuit of the cycloconverter feeding a synchronous motor is shown in the figure. Cycloconverter inherently capable of power transfer in both sides. 4-quadrant operation is simple in this case. A cycloconverter in above speed ranges give high quality sinusoidal voltage output. The resulting current are also sinusoidal. The harmonic content of the current is small. Consequent effect of harmonic current such as losses, heating and torque pulsation are minimum. The line power factor is somewhat better because the machine power factor can be made unity. So, the last topic is current source inverter fed induction motor drive. The inverter fed synchronous motor have been very popular as converter motor in which the synchronous motor is fed from a current source inverter having load commutation. A synchronous motor, a stator current which is independent of the stator frequency. The motor also developed constant torque. The flux also remains constant. Therefore, by varying the stator current of the synchronous motor, we have flux control as well as torque control. When fed from a current source inverter, the synchronous motor can operated at leading power factor, so that inverter can be commutated using machine voltages. A load commutated CSI fed self controlled induction motor is very well known as converter motor. It has very good stability characteristics and dynamic behavior similar to the DC motor. When fed from a CSI, the synchronous motor is supplied with current of variable frequency and variable amplitude. The DC link current is allowed to flow through the phases of the motor. The motor current are quasi square wave if the commutation is instantaneous. The harmonic present in the stator current causes additional losses and heating. A current source inverter is capable of regeneration. No additional converter is required, and 4-quadrant operation is simple and straightforward. So, we stop here for today's lecture, and we will continue in next lecture, and in next lecture we start DC drives. So, thank you everyone and keep learning.